Okay, so today we're going to learn how to take a complicated circuit, combination circuit, and simplify it down to one resistor called equivalent resistance. Okay, this was circuit 6. If I take out light bulb A, what other light bulbs go out? B and C go out. Current can't go here, and it can't do this. Okay, here's a rule. Current cannot go through the same direction. Sorry, can't go two different directions through the same wire. Okay? If I took out light bulb B, what other light bulbs go out? If I took out B, A and C would still stay on. Current can go through here. Okay? If I took out light bulb C, what other light bulbs would go out? Nothing else would go out. We could still go through A and B and get back home. Good? Okay. So what I'm going to do is I'm going to try to simplify these. So I have 2 ohms here, I have 2 ohms here, and 2 ohms here. I want to simplify, reduce these down to one resistor, the equivalent resistance, but there's a process. Okay. So if I take out A, that knocks out both B and C. I don't want to start there, that affects everything. If I take out B, C stays on. If I take out C, B stays on. So B and C are wired how? In series or parallel? Everybody okay in parallel? Current has a choice here. If there's a junction, that kind of screams you have parallel. I'm going to wire these two in parallel. I'm going to find the total resistance of these two. So in parallel, that's 1 over R is equal to 1 over 2 plus 1 over 2, excuse me, 2 over 2. Find the reciprocal 1. Okay with that? This next thing I'm going to tell you to do, you're not going to like it. You're going to fight me like, that's stupid. Why do I need to do that? I'm going to highly, highly, highly encourage you to redraw the circuit because I know where we're going to go tomorrow. Okay? This is an important process. I'm teaching you step 1 today. The next steps will come tomorrow. Okay? So, light bulb A has 2 ohms. Light bulb BC has 1 ohm. Redrawing the circuit. I've simplified this to that. Good there? Wired in parallel. Now, if I take out A, does that turn off B? If I take out BC, does that turn off A? It has to, it's not just if current touches it, it has to go all the way back home, start positive into negative to do a complete circuit. So it kills A. Okay? So A and BC are wired how? In series. Okay? So finding the total resistance in series, 2 plus 1. Redraw the circuit. ABC, 3 ohms. That is the total or the equivalent resistance of this circuit. It's as if this battery is hooked up to a 3 ohm resistor is what this behaves like. The equivalent resistance. Good with that? Good? This is circuit 7. If I pulled out light bulb A, what other light bulbs go out? C goes out. Everybody okay with that? Can't do this. If I pulled out light bulb B, what other light bulbs go out? A and C still stay on. If I pulled out light bulb C, what other light bulbs go out? B stays on. A goes out because it can't do that. Just because the current touches it, has to go through it and all the way back home for it to turn on. Good? So, each of these has 2 ohms. What I'm going to do first, if I pulled out A, it affects C. If I pulled out C, it affects A. B isn't affected by anything, so I'm going to simplify these two. These are wired out in series. Okay, so I'm going to redraw the circuit. So this is AC, and this has a resistance of 4 ohms, and then here's B, so 2 ohms. That. If I took out B, AC stays on. If I took out AC, B stays on. So B and AC are wired out. These guys are wired in parallel. So 1 over R is equal to 1 over 2 plus 1 over 4. That is equal to 3/4. Remember to find the reciprocal. So 4/3. Apologize. Markers are dying. So ABC has 4/3 ohms. The equivalent resistance is 4/3. Good with that? Questions there, points of confusion. Okay. All right. Kick it up a notch. I pulled out light bulb A. What other light bulbs go out? Everybody okay with all of them? Can't do this. The current's going 2 different ways in one wire. If I pulled out light bulb B, what other light bulbs go out? A, C, E stay on, B goes up, B and D go out. If I pulled out light bulb C, what other light bulbs go out? Everybody stays on. If I pulled out light bulb D, what other light bulbs go out? B goes out because just because it touches it, it can't come back, have current go in two different ways in one wire. If I pulled out light bulb E, what goes out? Everything goes out. We getting the feel for this? Okay. So, we need to group these in a systematic way. The order of operations matters. Okay. I'm not going to mess with 4 and 5 because that affects everything. Don't touch that. Like, stay away. That doesn't happen till the end. Okay. Okay. So 2 affects 1, and 1 affects 2. You okay with that? So these two are wired how? Series. Okay. And I'm going to redraw. Oops. Where I put this resistor on here does not matter. Now, before I go on, a popular wrong answer is doing this. 1 and 6 are in parallel. Just because they're drawn geometrically parallel doesn't mean you should consider them as parallel. If I take out 6, 1 stays on. If I take out 1, 6 stays on. However, if I take out 1, it affects something outside of that grouping. If when you take out a light bulb, it affects something outside of that grouping, pull back, re-strategize. Not a good path. I'm trying to teach you like the logic process for like how do I group these. Does that make sense? Why you would want to do 1 and 2 and not 6 and 1. Okay. So if I pulled out light bulb 3, what other things go out? Everything stays on. If I pulled out 6, everything stays on. Okay? So these two are wired in parallel. So 3, 6, equal 1/2. R is equal to 2. Okay with that? Redraw. Pulled out the 4. What else goes out? We're good with 2 and 5. If I pulled out the 2, what else goes out? 4 and 5. If I pulled out the 5, 4 and 2 goes out. So these 3 are wired how? Series. So all I do is straight up add them. 11 ohms. Good at that. Okay. When I was in high school, this was a breath of fresh air. The math is easy. It's more of a puzzle. Okay? So as long as you can figure out the logic gates, it's like, hey, I can do this. Okay? Good with that? Questions here before this goes away? I want you to redraw because what's coming next tomorrow, you'll need the redraws. Okay? I want you to strategize. The groupings. You got something? All right. I don't want you to do this, I'm just doing this for the sake of time. You know, why are those in series? You okay with that? You know, why are these in parallel? You can do both of those same step. Okay. Here's two popular errors. Okay. I did this in high school. I thought if I pulled out A, B and C stayed on. Like, look. I had current going two different directions in one wire. Okay. The other popular error is like, oh, look, I can go B, C, red in parallel. Because I pull out B, nothing else goes out. Pull out C, nothing else goes out. Pull out red, nothing else goes out. Problem is, if I pulled out B and C together, A goes out. So I need to deal with that before I bring that in. Okay. So that's in parallel. No, that's in series. And then the last step is the black and the red are in parallel. Okay with that? I have another color. Parallel. Good? Not good. Okay, you have a worksheet for tomorrow, but okay. Going back to parallel. For the sake of time, is everybody okay with increases? You're adding another checkout line to Walmart. You're adding another hole to your water tower. You okay with that? Okay. What happened? Sorry. How your house is wired? You turn off your TV, the whole house go out? All right. So they're in parallel. What happens as you get more and more appliances turned on in parallel? Happens as your total current increases, yes? What happens if you have a lot of current going through a wire? Is that a good thing or bad thing? A lot of current. What happens to that wire? It. Oh, come on, kids. Give me something. All right. You'll be fine. You'll be good. Have that wire get really hot. Catch your house on fire. Everybody getting where I'm coming? Okay. So what we have are fuses to help us prevent that. Come on back here as you can see this. Okay, fuses are designed to be the weakest link. Or not. You can see it right there. That's fine. Okay, so this is gonna be my fuse. What I have in my hand is the fuse. It's designed to be the weakest link. Nowadays, we have circuit breakers that just control the temperature. You gotta be kidding me. Oh, it's going. No. Ah. We're not yet. Piece of junk. I don't know why. What is going on?
We're just gonna let this cool down.
Okay, so turn on one appliance in parallel. Turn on
We're in a minute.
one of my wires is not happy. One. Turn on a second appliance in parallel. It's smoking. Okay, and it blows the fuse. Okay. So, in cars, you have fuses. The little piece, they look like colorful buck teeth. Okay. Today we have circuit breakers. So trips a switch, you got to go back, flip it, make sure you turn off your stuff. Got worksheet due tomorrow. Where's the deal, yo?